I told you about uh, first law of thermodynamics is basically the law of conservation of energy. Okay. In simple words, we can say that energy can neither be created nor be destroyed. But this is very basic definition. We should look for the real definition which we are going to use here for the thermodynamic systems actually. So it says that according to first law of thermodynamics, in a closed system. So see it here, it's a closed system undergoing a thermodynamic cycle. The cyclic integration or cyclic integral of heat transfer is equal to cyclic integration of work transfer. So this is the equation of the first law of thermodynamics, that cyclic integral of delta W is equal to cyclic integral of delta Q when both are taken in consistent set of units. Consistent set of units. Okay. So this is important because I might have told you that earlier we were using calorie for the heat transfer and joules as the unit for the work transfer. So if we are using that, then we have to go for mechanical equivalent of heat. Okay, that is denoted by J, which we are not using here because we are talking about the consistent set of the units. We are considering the SI system of the units. So in SI system of units, both work and heat, both W and Q, they are either denoted given the unit joules or kilojoules or megajoules. Okay. I told you the first law of thermodynamics. Now, suppose there is a cycle which is taking place from 1 to 2, 2 to 3, and 3 to 1. We started from point number 1 and reaching back to the, while following this path, we reach back to point number 1 only. Okay, started from here. So you can see there are three processes. So when we see the three processes and we apply this particular equation, cyclic integral of delta Q is equal to cyclic integral of delta W, then we can write Q1 to 2. This is the heat transfer term for the process 1 to 2. For this particular process, I have written this value of heat transfer. Then this is for the next process 2 to 3. This is for the process 3 to 1. It is also heat transfer. That should be equal to work transfer in the process 1 to 2, work transfer in the process 2 to 3, and work transfer in the process 3 to 1. So basically, this is the first law of thermodynamics when we are taking whole cycle, but now we are writing it for each of the processes, so that when I write each term for each of the process, the initial state and the final state is same. So it's a closed cycle actually. It's not only a closed cycle, it's also a closed system. We are writing it for the closed system also. But this um, if we talk about the conservation of the energy principle, this will also be applicable to the open system. Okay, it's not like that it won't be means applicable to the open system. In open system also, we can always say that the energy which is entering into the system is equal to energy which is going out of the system. So that is the basic first law of thermodynamics. Okay. So uh, this I discussed that it was due to J.P. Joule that he gave the equivalence of the work and heat during 1840 to 1849, and this is the first law of thermodynamics for a closed system undergoing a thermodynamic cycle. Repeatedly, I am telling you so that you understand it. Now, this was you can say this is the for a thermodynamic cycle. Now, suppose I want to um, make this law applicable for a change of state or for a process. Okay, you can see the heading. What is the heading? Heading says first law of uh, first law for a closed system undergoing a change of state. When I say change of state, man, that means I am talking about some process. Okay, for any one process or any two processes which may not be ending at the same point actually, because if there are two or three processes but the final state is different from the initial state, then this equation cannot be applied in that particular case. I cannot apply that this particular equation of the first law of thermodynamics for a thermodynamic process actually. Okay, so now let us see what change we need to do in this particular case. Now you just see what I have done. This is the statement for a cycle. You can see it here. This is the first law of thermodynamics for a cycle. Now what I did, I have brought this delta W on the left hand side. So now you can see what I get. I get delta Q minus delta W, and its cyclic integral. Just focus it here. Okay. The cyclic integral term is here. And the right hand side is 0. So what does it imply? Once again, look at this particular equation. Just focus here. What does it tell actually? Can anybody tell me? What is the implication of this left hand side and the right hand side? What does it implies?
That the total heat supplied to the system will be equal to the total work done by the system.
That's true. That is the first law of thermodynamics for a cycle actually. Anything else?
Internal energy constant रही, I guess.
See, where is the internal energy term here? It's not here. See, you see, read here. No, you read here. Let us see the right hand side of the above equation. It is 0. The left hand side can only be 0 if it's a property. It is so because only cyclic integral of a property can only be 0. Okay. So let us see in the next slide what I have written here. You would be able to understand it in a better manner actually. Once again, it is a repetition of the previous slide. Okay. Now you see it here. What I have written here is, for example, if you want to calculate the value of cyclic integral of delta T, I have put a question mark here, and you know the value. I have put a question mark for dP also. Okay. Now these T and P, if I take the value of both these means for the cyclic integral of pressure and the cyclic integral of temperature. If I am taking the cyclic integrals, means this system is undergoing a cycle, then the right side is actually equal to 0. You know this, that in case of a property, if you take the cyclic integral, means if this is a cycle, if I am drawing this PV diagram, I start from here, I come up to this particular point, then go back to the initial point. This is point number 1, this is point number 2. So I know if I am reaching the same point 1, the system is completing a cycle. And in that particular case, if you take any property, that will come out to be 0. So now you compare this equation, okay, this equation with this particular case here, for the case of cyclic integral of dt. What does it shows? This value on the left hand side, this value, cyclic integral of delta q minus delta w, I am talking about this is coming out to be 0. If you see, delta q is a path function, delta w is a path function, but if I am taking their difference and taking its cyclic integral, then the value comes out to be 0 on the right hand side. And this is applicable if the left hand side is a property only. Is it clear? Okay. So that means this whole thing, this delta q minus delta q minus delta w cyclic integral, if I'm calculating, if it is coming out to be 0, then this whole is a property. So next slide will make you the concept more clear. So what I have written here, I have written cyclic integral of delta q minus delta w is equal to 0, or I can say, I can also write cyclic integral of derivative of some property, exact differential of some property is equal to 0. See, read it here. See this term I am talking about. So I am saying that this term is some sort of property because the right hand side is coming out to be 0. Okay. So that is, I can say, if it is a property, then delta q minus delta w cyclic integral can be said equal to dE. Okay. So d comes from this because it's a property, so it has to be exact differential, and E is that property. E is that property, okay, which is for which the value comes out to be 0. And this is nothing. This is actually energy. So I can always write, if I remove this cyclic integration sign, then I get this value delta q minus delta w is equal to dE. So it means for any process, if I am talking about any process, because this equation when I have written, this is for a cycle, you know it, this is for a cycle. But when I remove this integration sign, cyclic integration sign, and I only leave it in the differential form, then I get this equation, delta q minus delta w is equal to dE. Okay, and this is valid for a process, because now when I will integrate this equation from state point 1 to state point 2, then I can calculate the value of delta q in that equation, delta w in that equation, and dE in that equation. So if you see here, you can see this is what I have done here. Okay, I have considered any particular process 1 to 2, and I have integrated this equation delta q minus delta w is equal to dE for the process 1 to 2. Okay, so what do I get? I get delta q for the process 1 to 2 minus w for the process 1 to 2 is equal to E2 minus E1. So even if you initially don't know that what is this E, later on it will come to the picture actually. The above equation clearly shows if Q is the amount of the heat transferred to the system and W is the amount of the work transferred from the system during the process, the net energy transfer Q minus W will be stored in the system. Is it clear? So basically what we are saying, if Q is the amount of the heat transfer to the system, means if I am considering, suppose this is the system, okay, and let us say during a particular process, heat Q1 to 2 enters into the system, and let us say work W1 to 2 goes out of the system, and suppose the value of Q1 to 2 is 50 and W1 to 2 is equal to 25, then how the balance of energy will take place? That means 25 balance energy which is not going outside has to be inside only. So 25 is here, which remains within the system boundaries only. So this is a sort of stored energy of the system. So this is a stored energy of the system. So energy in storage is neither heat nor work. I have already told you when we discussed about the concept of work and heat transfer, there were certain important points which I discussed with you. I told you heat transfer and work transfer are only observed at the system boundary. Okay, when they cross the system boundary, they are the path functions. Okay, they are inexact differentials. So I told you certain points. So you should always keep those points in your mind, that work is an energy in transition, heat transfer is an energy in transition. So here this energy which is now stored within the system boundary, it is not in transition, it is stored energy. Okay, so this energy which is stored is neither work nor heat, it is neither heat nor work, and is given another name which is known as internal energy, or simply energy of the system. Okay, and this energy for this process 1 to 2 we have written as E2 minus E1. Is it clear to you people? Any questions about this?
No,
No,
sir.
sir.
Okay, all right. So now let us discuss the application of first law of thermodynamics for a process to a thermodynamic cycle undergone by a closed system. Now, once again, I have taken that particular initial cycle which we discussed earlier. So process 1 to 2, process 2 to 3, process 3 to 1. So three processes are there. Okay. So now what I have written the cycle. If I have to write the name of the cycle, it is 1, 2, 3, 1. Okay, starting from 1 goes to 2, goes to 3, and then once again we come back to point number 1. So the name of the cycle is 1, 2, 3, 1. So I can apply the this particular equation, cyclic integral of delta q is equal to cyclic integral of delta w. So I can apply this. So this is valid for a thermodynamic cycle. Okay. So if I have to use this equation for a process, then I will write this delta q minus delta w is equal to dE. Okay, this is valid for a process. So if I have to take the process 1 to 2, I can integrate this particular equation here for the process 1 to 2. So I will write delta q integral 1 to 2, delta w integral 1 to 2, dE integral 1 to 2. Okay, and then I get this particular equation u1 to 2 minus w1 to 2 is equal to E2 minus E1. Similarly, I can apply this for the process 2 to 3. I get Q2 to 3, W2 to 3, E2 minus E3 minus E2. And then for the process 3 to 1, Q31 minus W31 is equal to E1 minus E2. Now you see it. You add the left
Sir,
hand side
E1
and the
minus
right hand.
E3.
Yeah, that's a mistake. E1 minus E3. Okay. E1 minus E3. Okay. So now you can see, if you take the left hand side, what do you find? You see that Q1 to 2 plus Q2 to 3 plus Q3 to 1 minus W1 to 2 plus W2 to 3 plus W3 to 1 is comes out to be 0. That is, it's a sort of algebraic sum of heat transfers minus algebraic sum of W. That comes out to be 0. So, or I can say cyclic integral of delta Q is equal to cyclic integral of W. So basically, we took the three processes which are occurring in the cycle and proved, we started from a process, and what we proved this applicability of the first law of thermodynamics for a process, that it is also valid for a cycle actually. This is clearly visible in this simple calculation actually. So basically, uh, if you know the heat transfer and the work transfers for a particular process, you know the change in the energy which is happening during that particular process. And when you add all these three processes or four processes or five processes which are occurring in the cycle, then the sum of the all heat transfers is actually equal to sum of all work transfers. Okay. So this is a sort of simple proof of the application of first law of thermodynamics, or you can say it's a application also and a proof of the process for a cycle actually. Okay. Now, what are the different forms of the stored energy? Now, we are talking about E now. This E stands for the energy. I think somebody wants to join. Is it? Just wait for a second. Yes, Vishal. Vishal, why are you late? Okay. So now we have two types of the energies. One is the macroscopic and other is the microscopic energy. Now you can see what has been shown here. This diagram 4.6 shows there is a fluid mass. Okay, this is the fluid mass. This is moving. There is random thermal motion of the molecules which is shown here. This is the mass of the system. This is the average height of the fluid particles from some datum actually. So this is given here. This is shown in the diagram. Now let us discuss about the macroscopic and microscopic energies of the system. Okay. The macroscopic energy mode includes the macroscopic kinetic energy and potential energy of the system. Macroscopic means we are taking the energy of the system as a whole actually. So let us consider a fluid element of mass m having the center of the mass velocity v. The macroscopic kinetic energy ek of the fluid element by virtue of its motion is given by half mv square. So basically, the molecules are moving. We are considering them as a whole, and v is the velocity. So the kinetic energy, which the molecules, all the molecules are having on average, is given by half mv square. This kinetic energy part. Similarly, we can write the potential energy term, which will be given by mg z. Z means the average height of the uh, total mass of all the particles. Okay, so that is these are the two microscopic macroscopic parts. Now let us talk about the microscopic part. Now, what is microscopic? The microscopic energy mode refers to energy stored in the molecular and atomic structure of the system, which is called the molecular internal energy, or simply internal energy, and it is customarily denoted by the symbol small or capital U. If you are using capital U, it will be total internal energy. If you are using the small u, it will be specific internal energy. Okay. So matter is composed of molecules. Molecules are in random thermal motion for a gas with an average velocity v, constantly colliding with one another with the walls. So this is shown the kinetic energy part. Okay. This is rotational part. This is vibrational energy, nuclear binding energy, electron energy. So these are some parts of the at the molecular level actually. So if we take all these sorts of the energies, if I am representing all these microscopic energies by epsilon, okay, represents the energy of the one molecule. Then epsilon is given by translational, rotational, vibrational, chemical, electronic, and nuclear energies. So total energy U will be given by N into epsilon, where N is the total number of the molecules in the system. Okay, but I would like to tell you here that you should not worry about the molecular level. In the first lecture itself, I have told you we are interested in the macroscopic part of the energy or the macroscopic nature of thermodynamics. We are not going at the molecular level. So we only need to know the value of capital U or small u. We don't need to worry about what is n into epsilon. So this is not needed at all here. This is just for your information. So now what? See, once again, I am telling you this was the equation of first law of thermodynamics for a process. This is valid for a process. So we are talking about this E. E is the energy actually. So what is this E? E is actually equal to kinetic energy of the molecules taken as a whole. This is the macroscopic part, and U is the microscopic part. Okay. So, but we are calculating the U as the total energy, total internal energy of the system. We are not worried about the internal energy at the molecular level. So we will be calculating U by some equation, which is actually written here also. U is a function of T only for ideal gas. Okay. So it's for ideal gas that we can always calculate the value of the internal energy. Okay. So Ek, Ep, and U refer to the kinetic potential and internal energy respectively. In absence of the motion and the gravity, means if we are considering the kinetic energy and the potential energy as negligible or zero, then we can say that E is equal to U. Once we say this, we will write the equation of the first law of thermodynamics for a process as delta Q minus delta W is equal to du. So this is what we can write as the equation. And in most of the cases, you will find that we will be using this only, this equation only. Okay, so this is basically the first law of thermodynamics for a process. So this is valid for a process. If by chance we are given with the kinetic and potential energy terms, only then we should use that in the numerical problem. So you can see it here. I have written once again this equation delta Q minus delta W is equal to dE, where it is equal to derivative of the kinetic energy part, derivative of potential energy, and derivative of internal energy. So in the absence of kinetic and potential energy terms, this is term dE comes out to be du only, and this U is an extensive property called as the internal energy. If I divide this capital U by m mass, then it becomes specific internal energy, and the units of U is kilojoules, whereas for small u it is specific internal energy and the units will be kilojoules per kg. Any questions till now? Okay, so basically you need to remember this particular equation only. Delta Q minus delta W is equal to du, or you can, if you want to remember, you can also write it as dE, but mostly we will be not discussing about kinetic energy part and the potential energy part. Now Joule's law. Now what is Joule's law? Joule's law is, it states about the internal energy. It is proportional to the temperature for ideal gases. Okay, so we talk about the ideal gases for which the equation PV is equal to MRT is valid. Okay, you know about this particular equation. So if it is the ideal gas for which PV is equal to MRT is valid, there we can say this internal energy is a proportional to temperature. Or if I remove this proportionality sign, I can say small u will be equal to Cv into T. Okay, where Cv is the constant and is known as specific heat at constant volume, and U is the specific internal energy in kilojoules per kg. If I have to calculate the capital U, what I will do, I will multiply by mass here, and the total value of the internal energy will come out to be mcv t. If I want to write this equation in the differential form, then I can write du is equal to mcv dt. So once I integrate this equation, I will say that u2 minus u1 is given by mcv t2 minus t1, which is the change in internal energy u2 minus u1, and it is equal to mcv t2 minus t1. So not to worry much about this. You just have to remember the equation du is equal to cv dt. Okay. So once you have not written m here, so it's a specific internal energy. If you write the m here, if you introduce m here, then it becomes this u will become the total internal energy of the system. So it's your understanding basically. But if we are writing du, it means it's small u, so it should be cvdt. If you are writing capital U, then you should write mcv dt, and then you can integrate it to get the value as shown in this particular equation. Okay, now we will discuss about heat transfer in various processes. See, now we have already calculated the value of change in internal energy for a, means the formula for the internal energy for a gas is known to us. We know that dU is equal to mcv dt. This is known to me. Similarly, I have also calculated the value of work transfer for the processes which we discussed, like isothermal, isochoric, isobaric, reversible adiabatic, and polytropic processes. So we have calculated the value of the work transfer in those processes. Now we want to calculate what is the value of the heat transfer in all these types of the processes. So let us see. So first process which I am considering here is a constant volume process. Constant volume process. Okay, or isochoric process. Now you know, for a isochoric process, once again let me remind you, I am here talking about PdV work. See, if you see this particular equation, delta Q minus delta W is equal to du or de. Okay, here it is written as delta W. Now this W could be PdV work. Okay, could be shaft work, could be some sort of electrical work, could be flow work. Okay, could be some other, could be magnetic work. Okay, so basically here we are talking about the PdV work only. Okay, so you should always remember that this delta W is for a simple compressible system. I am talking about a simple compressible system. Whenever I am calculating heat transfer here in this topic, I am considering that this delta W is only PdV work in a simple compressible system. So you know, if it is a constant volume process, it's a simple compressible system, then in that particular case work transfer is given equal to 0. This is the PV diagram, vertical line. Either you go from 1 to 2 or you move in the upward direction, keeping the volume constant. So it's basically uh, there won't be any work transfer. You know about it. Now let us see what is the gas equation. Once again, PV is equal to mRT. Now if V is constant, I can take this V on the right hand side and T can be brought on the left hand side. So I get P by T is equal to mR divided by V. So just see, for a particular gas, the value of M into R will always be constant. So this value is already constant. And we are saying that it's a constant volume process. So whole right hand side will become constant. So that means in case of constant volume process, P by T will be equal to constant, or I can say P is proportional to T, and this is actually Gay-Lussac law. So it's Gay-Lussac law, or I can write it as P1 by T1 is equal to P2 by T2. So basically, whenever you are given with the constant volume process, you are given with the pressure and temperatures at one point and other point it is not known. Means three parameters are known and one parameter is not known. You can always calculate the fourth parameter or the fourth property using this particular equation. So what is the value of change in internal energy? Change in internal energy have only a single equation, dU is equal to mcv dt for every process. So u2 minus u1 will be given by mcv t2 minus t1. Okay. So mass is in kgs. Cv, the value is kilojoules per kg Kelvin. Temperature is considered in Kelvin. So you can see the value of U will come out to be in kilojoules. You can see kg will cancel out from kg, Kelvin will cancel out from Kelvin. So we are left with kilojoules only. Or if I want to write it on in the terms of specific internal energy, then I remove the value of M here. I'm not writing any M here. So the unit comes out to be kilojoules per kg. So now I want to calculate the heat transfer for this constant volume process from 1 to 2. So from first law of thermodynamics, for a closed system undergoing the process, I can always write delta Q is equal to du plus delta W. Now this value is 0. Delta W I have already told you. So it gives me delta Q is equal to du. So what is the value of heat transfer in this particular case? Heat transfer will be given by mCv T2 minus T1, which is equal to change in internal energy. So this is the final value of the heat transfer for a constant volume process. Now I go for the constant pressure process, isobaric process or isopistic process. So once again, first of all, what I will do, I will write the equation of work transfer. This is the value of the work transfer for a constant pressure process given by P V2 minus V2 minus V1, which can be written as MR into T2 minus T1. It's quite simple. Okay, you need to remember this actually. And once again, PV is equal to MRT. Now P is constant in this particular case. So what I will do, I will take V by T on the left hand side, whereas MR by P is on the right hand side. So this all becomes constant. So this is a constant term. So that means I get the V is proportional to T, and V proportional to T is Charles law. Okay, Charles law. So once again, if this is the process, constant pressure process, it is given to me. And if I know, suppose V1, V2 and T1, so I can always calculate the value of T2 using this particular equation, okay. So this is Charles law. Now the question is, what is the value of the heat transfer? So W is already given to me. W we have already calculated for the from the PDV work equation. Now change in internal energy. Change in internal energy, once again same formula, U2 minus U1 is equal to mCv T2 minus T1. This is the formula. So what I can do is I can write this equation from the first law of thermodynamics, which is given by delta Q is equal to delta W plus du. From this equation, when I integrate this equation, I write Q1 to 2, W1 to 2 plus U2 minus U1. So put the values of W. W is P V2 minus V1. U2 minus U1 is mCv T2 minus T1. And this P V2 minus V1 can be written as MR T2 minus T1. So this T2 minus T1 can be taken out of the brackets, and M can be taken along with it. So M into T2 minus T1, and inside we are left with R plus CV. And you remember the equation Cp minus Cv is equal to R.
R.
So from there you can write the value of Q1 to 2 as mCp T2 minus T1. This is the repetition part, and here I have written that equation. So the value of heat transfer is equal to mCp T2 minus T1. What is Cp? Cp, you know, is the specific heat at constant pressure. So let us move to the constant temperature process now, which is isothermal process also. You know, for the isothermal process, PV temperature is constant. I can write the gas equation here. Okay. So from the gas equation, because temperature is constant, so this right hand side, this whole term will become constant. So I can write PV is equal to constant. And what is this? This is Boyle's law actually. So P is inversely proportional to 1 by V. Or I can say P1 V1 is equal to P2 V2 is equal to constant. This is what I can write. And this is the representation of the constant volume, constant temperature process or isothermal process, where I can write PV is equal to constant or T is equal to constant. Okay. So once again, what will be the change in the internal energy in this particular case in constant temperature process?
0.
0. It would be 0 because there is no change in the temperature, and the for internal energy, if it's a gas, we know the formula is mCv in dt, and the value of dt is 0. So once dt is 0, That means change in internal energy is equal to 0. So you can see now what is the value of W for constant temperature process. Constant temperature process W is given by this particular equation. P1 V1 log natural V2 by V1, and this is the value of the U2 minus U1, and we know that this value is 0 because T1 is equal to T2. And once again applying the first law of thermodynamics, delta Q is equal to delta W plus du is 0. So we are left with Q1 to 2 is equal to W1 to 2, and this equation means the value of W1 to 2 can be put here. P1 V1 log V2 by V1 can be written as MRT log V2 by V1, okay, or P2 V2 log V2 by V1 MRT log V2 by V1, and so on. Means you can write this term here as log P1 by P2 also. So it is MRT1 or MRT2 multiplied by log natural P1 by P2 or log natural V2 by V1, means any of these can be taken. So I hope this is clear to you. So three processes we have discussed. One more process I will discuss briefly actually. Now I am coming to this reversible adiabatic process. When I say reversible adiabatic process, you know there is no heat transfer. Q122 is equal to 0 or delta Q value is equal to 0 because it's adiabatic process, and in an adiabatic process there is no heat transfer. And one more thing, it is reversible here. Okay, when I write reversible, I have already told you that normally we don't write reversible with the other processes, but they are reversible in nature. Only then we can write all these equations for those processes. Now, what is the meaning of the reversible in case of adiabatic process? This is what I have written here. No friction within the system boundary. No friction within the system boundary. Okay, because friction makes a process irreversible. So if there is friction within the system boundary, it will make the adiabatic process irreversible. So that has been neglected. So now let us see. I can apply this first law equation. Delta Q is equal to du plus pdv. Now first you must have observed when I am discussing all these processes, first I am telling you the relationship between various properties. For example, if it is a constant temperature process, I told you P into V is equal to constant. Now what similar means equation would be valid in case of adiabatic process? You know PV is equal PV raised to power gamma is equal to constant. So from where that comes actually. So let us see. So delta Q is equal to du plus pdv. I can put the value of delta Q as 0. So I am left with du plus pdv is equal to 0. Now what is the value of du? It is equal to mcv dt plus pdv is equal to 0. Now I know this equation. If I want a relationship between pressure and volume, you already know this equation. PV is raised to power gamma is equal to constant, but how to get it? Now in this equation, you have V here, you have T here, but I want a relationship between pressure and volume. So what I will do, I would like to remove this dt from this particular equation. Now let us see at this equation. This is the gas equation, ideal gas equation. PV is equal to MRT. So what I will do, I will differentiate this equation. When I will differentiate this, I can initially take P as constant, then it becomes PV because you will apply a product rule here. Okay, so PdV plus VdP is equal to MR because MR is constant dt. So this is the value. This is on differentiation. On differentiation, you will get this particular value. PdV plus VdP is equal to MR dt. So I can calculate the value of dt from here, which comes out to be PdV plus VdP divided by MR. So let us say this is equation number 2, and this was my initial equation, which was written on the previous slide. You can see it here. This is the equation. I am talking about this particular equation. mCv dt plus PdV is equal to 0. Okay. So mCv dt plus PdV is equal to 0. This is nothing but this is change in internal energy. This is work transfer, and this is the value of heat transfer. So this is first law equation, FLT. This is first law equation, and this is the value of dt. So what I will do, I will put the value of dt here. Okay. So you can see it here. This is the dt, and this is first law equation. From both these equation, what I will do, I will put this value of dt here. So mCv, this is the value of dt now. You are putting it here. PdV plus VdP divided by MR plus PdV is equal to 0. So M and M will cancel out. So we are left with CV into PdV plus CV into VdP plus R. Now this R, when we take LCM, this will go here, R PdV. So now we can take these two terms, these two PdV terms, this term and this term. So PdV is common in both of them. So we will get CV plus R PdV plus CVV VdP, this term. Okay. So this comes out to be 0. So this becomes CP PdV plus CV VdP. So Cp PdV plus Cv VdP. So you divide the whole equation by Cv. So when you divide the whole equation by Cv, this Cp by Cv, it is a ratio of specific heats, becomes gamma PdV plus VdP is equal to 0. And then you divide by PV. So what will happen? P and P will cancel out, V and V will cancel out. So we are left with gamma dV divided by V is equal to dP by P. Now you integrate this equation. So what do you get? You integrate and you will get gamma log V minus log P plus log C. This is a constant value. So I can bring it on the left hand side. So I will get, you know the rules of the logarithms. So you will get this particular equation. Then you can take the anti-log on both the sides and you get this particular equation. PV raised to power gamma is equal to constant. So I think it's 2 now. So this much is sufficient for you. I can show you these two slides also. Here I have calculated the value in terms of TV raised to power gamma minus 1 is equal to constant. And here I have calculated in terms of pressure and temperature. This is, so when you will see the videos, you can see the last 5 minutes and you can read these two. Okay. And you would be able to know the relationship in three terms. So these are the three relationships which you need to remember actually. PV raised to power gamma is equal to constant, TV raised to power gamma minus 1 is equal to constant, and P divided by T raised to power gamma over gamma minus 1 is equal to constant. So these are the three relationships which are valid in case of reversible adiabatic process. And when you calculate the value of Q, Q you know should come out to be 0. So I have calculated, we can discuss it in the next class. Just wait for a minute. If you have any questions, you can ask.
Sir, I had some doubts in tutorial sheet.